So here's the overall structure of this quote-unquote talk. First, I'm going to tell you all about what Mathly is for the first section, and you should please feel free to interrupt me and just ask questions whenever you want. And then we're going to have a little, I would say, mock demo thing, except you're actually going to not pretend to be students, but be your actual selves, because we're going to talk about some math in a slightly different framing than you're accustomed to, perhaps. And then I'm going to wrap up by talking about how the types of techniques that we use at Mathly can translate into college mathematics courses. So let's see here. So Mathly stands for Serious Mathematics Infused with Levity. And it's an intensive residential summer program for mathematically talented high school students. It's 5 weeks long. The daily schedule is pretty much 4 hours of morning class, then you have lunch and relax. There's a daily gather, which is a communal activity for all the classes. Then everybody goes to dinner. There are 3 hours of evening class. And at least one of those 2 classes, either morning or evening, is a problem session where the problems were generated in the previous class or classes. In terms of the 5 weeks, there are 2 weeks that are common material. We call that root class, and that's theoretical linear algebra and graph theory and combinatorics. Some basic probability, usually also the definition of a group, maybe a little bit of number theory also. There's 1 week of chaos, which is lots of short topics classes held sort of all at the same time all over the place. And then 2 weeks of branch classes, which are focused classes. And so, for example, last year one of the classes was on topological graph theory, and the other one was math of paper folding. And this year one is going to be convex geometry and polyhedra, and the other one's going to be chaotic dynamical systems, fractals, stuff like that. But they vary from year to year. Where do the students come from? There are 2 ways to answer that. One is, how do you get them? So they have to fill out a short form and an not a short form, and those select for enthusiasm and general attitude. There's an exam assessing readiness, and I have a pile of those. You may want one because it's got lots of fun problems. And that selects for ability to contribute to IBL class discussion, both in terms of creativity of thinking about things and in terms of communicating one's ideas. And then they have to have a letter of recommendation so that they're not making up who they are. The other way you could answer this question, where do they come from? We have applications originating from at least 22 US states and 17 other countries throughout the Americas, Europe, and Asia. And this year the participants come from 9 US states from essentially all over the sectors of the US and 5 other countries. So what is the class structure like? This is where the IBL part comes in. So we don't have any pre-prepared guidance for the students. We don't give them any textbooks. We don't give them any worksheets. We essentially begin with a sort of Socratic method where we ask them questions. And we have a guiding philosophy of sort of put down the chalk, meaning if you've been talking and the students are starting to talk, you just put down the talk and you let them do as much talking as they want. We often turn it over at times like that to group or collaborative work on problems, where the problems are things the students have decided they want to work on. And we regularly have student presentation of ideas and conjectures and results, often stemming from a previous problem session. So like, the first thing that might happen in the morning is that a bunch of students will present what they did the previous night to other students who might have been working on different problems. In terms of what we try to get our instructors to do, and I should mention that we have 2 kinds of instructors. We have lead instructors who are mathematicians with PhDs and prior experience with inquiry-based learning. And we have apprentice instructors who are undergraduates and graduate students who teach directly under supervision of the lead instructors and get pretty much daily feedback on how they're doing. So we try to interrogate student understanding, meaning it's not enough for a student to say, yeah, I get it. They have to demonstrate that they get it. And if you, as an instructor, have some plan as to what's going to happen and students are having fruitful ideas, you just go with it. Who cares what your plan was? They're learning math, they're going to get stuff done, it'll be great. And we record pretty much every fruitful conjecture and fruitful question that comes up that isn't exactly quite on the topic of what the mainstream of the class at that moment is, and we reserve them for a problem session, and then everybody gets to work on them later. Oh yeah, so what is the culture of a class like? So we want everybody to have the chance to discover things, and of course everybody comes to a class having a slightly different background. So somebody may have already known the problem that has been just posed to them, and they're asked to not actually answer the question or problem until they've given other people a chance to experience it and play with it. So they don't want to give anything away. We try to have check-ins to make sure that everybody's on the same page so nobody gets completely snowed and lost for too long. And we really do try to ensure that all students participate verbally at the board, in groups. If students don't naturally even out their participation, we do things like have little lists in the corner of the board saying who hasn't been to the board lately, and then they know that they should try to find an opportunity to go to the board. If students are dominating, we squash them. If students are being quiet, we try to encourage them to be slightly less quiet. Not like to make loudmouths out of quiet people, but like to make sure their voices get heard. So then we actually try to disseminate IBL in the following ways. Okay, so approximately 10 times as many applicants as participants, and every applicant gets a copy of the EAR. And the EAR is kind of the worksheety kind of IBL, right, where it leads them through things to produce results. Some of our staff run activities for attendees at math competitions in IBL style. We have little mini flyers. They're like quarter sheets, and they say Mathly on the front. But on the back of each one of them is sort of an open-ended kind of problem for them to play with, and we have like 4 different backs. So we'll go to competitions and be like, free math, and people are like, oh, can I collect them all? That kind of thing. We also mail flyers to competitions because we can't go to all of them. And the people who are the apprentice instructors tend to take their IBL skills back into the community, meaning that you have somebody who did this as an undergrad, and when they're in grad school, they're supposed to run a recitation session, and then they try to run it IBL style. Also, past participants give us feedback saying that they are disappointed if they get to college and they're expected to not speak in class. And they clearly respect IBL classes, and they sort of start to expect them after a while. Okay, so this is a placeholder slide, so we can try to have sort of a demo. So what I want to do is tell you a little bit about what might happen in the first couple days of class, and then actually pose a question to you the way I would pose it to them. Whereas if you were students in the class, I would be like, okay, hold back if you know the answer, but we've only got like 10 minutes for this, so don't hold back. Just, say what you think. Oh, here's another cultural thing. At Mathly, students don't generally raise their hands. We encourage them to try to learn how to read the room and to just speak when it's appropriate. Okay, and then if they're queuing up, they'll start like raising their hands to each other so I'm not used to calling on people who raise hands, just to warn you of this. So one of the first things we do with them is pose a question much like if you've seen the Polya video, How to Teach Guessing, Let Us Teach Guessing. He poses this question about well, he doesn't pose it quite like this, but the question is, suppose you have a whole bunch of hyperplanes running through space, and you want to know what the maximum number of regions these hyperplanes divide space into. So this is a combinatorial problem only. So they'll play with this for a while, and they will get probably some partial results, maybe even in the first class, if not in the first couple classes. And so once they have this kind of idea of general position and stuff in their heads, I will pose a question to them like this. Okay, so we have all these flats. We call them flats, not hyperplanes, because we don't have that word yet. You have all these flats, and they intersect somehow, and you know that the number of regions has something to do with these intersection points. My question is, how do you find the intersection points? And what if you wanted to create a picture of this in the computer, like in some idealized way so that maybe you could rotate it? So what do? So I guess I'll write that down. I'm not saying anything yet. So what do you do?
I don't understand the first question in the sense of I'm not sure what they asked. Like ordinarily an intersection.
Someone's asking questions, but they're not asking questions, they're participating in the class.
But it won't be on tape, their voice won't be on tape.
So if you want to reiterate what they say.
Sure, we'll do.
Thank you.
Okay, so Gary is saying he wants to know what exactly this question is asking.
Okay, you don't want coordinates of point 3.
Maybe I do.
Well, I don't know. See, I don't know what.
I don't know what I want either in that sense. Tell me what you would like. Well, give just some answer, any answer.
Well, I don't have an answer yet because I don't really understand the problem. I need to think about what I would agree is the answer.
Okay, Gary needs to think about an answer. What he would count as an answer.
Intersection lattice.
You want an intersection lattice. I don't know what an intersection lattice means. So Tell me what you mean by that.
The collection of all intersections of the hyperplanes.
How do I find any of them? I don't have a single intersection of a
equation
hyperplane.
for each one, you just,
Wait, hang on. I need an equation for each one what?
each hyperplane.
Need equation for hyperplane. Okay. And then what?
Then if you have a collection of hyperplanes, you just look at the system of equations. You repeat the dimension, it doesn't mention the intersection.
Okay, so person whose name tag I can't read from here.
Jacob White.
Jacob White says he wants an equation for every hyperplane, and then he wants to solve the system of equations and find something about the dimension of the system and stuff like this. So my question is, what kinds of equations should we have for these objects? What should they look like? If we're going to find a set of equations and try to solve the system, we need to have some equations. So any suggestion for an equation that might work?
No exponents.
No exponents! Okay, no good. Because, yeah, wait, why don't we want any exponents though?
Makes things bend.
Makes things bend. Exponents make things bend. That's bad. We want things that are flat. So this is good. This is good. So we need something with no exponents. What else?
Well, actually, there are exponents, but the exponents are 1.
Okay, Gary says we have exponents, they're just 1. Okay, good. Suggested equations, anything?
Multiple variables?
Multiple variables. Okay, sure. I don't know what to write yet, though.
AX.
You want AX? Okay, AX. What's A and what's X?
A is a number, X is also a number, but we don't know what it is.
Not the equation yet, though.
No.
Equals
No, equals
0.
You want equals 0?
Start small.
Okay, so first thing I'm going to say is, come on, what is this an equation of?
One of the coordinate points.
One of the coordinate planes. Planes? Yeah, really? Seriously? I'm confused though, okay? Because like, I have a number, so you're saying that this one, you sort of implied this was a variable, right? So you say this is a coordinate plane. Why?
Excuse me, how many variables are we doing? I would like to start with 2 dimensions with x and y and work up. Holy said simpler problem first.
Okay, if you want to have 2 dimensions, we can do x and y.
Dimensions, but these are high school kids.
Oh, they already did it in n dimensions an hour ago.
Oh, we did that an hour ago.
Yeah,
But
an hour before this time,
But
they've
not-
already done it in n dimensions with no coordinates or anything.
No,
They did it combinatorially only.
I see.
Yeah, but great. If somebody says, well, I know the equation for a line or a plane, I'm going to be like, great. So you want to start with 2 variables? Great. 2 variables. What did the x and y represent?
Distances.
So, wait, 2 of you at once.
Sure. Distances from a fixed origin, sine distances from a fixed origin in 2 directions.
Distances from a fixed origin. What's an origin?
It's the point I'm going to pick, is the best, the one I'd like to start from, with all zeros.
So you're going to say this is all zeros. Except here it's, of course, just 0, 0. Okay. And wait, in 2 directions. Do you care which 2? You want perpendicular?
They're not parallel.
Not parallel? Okay.
Should be good enough.
Okay. Well, if they're maybe perpendicular, no, they're
You have a number times x, a constant, plus a number times y equals a third constant.
Okay, you have a number times x. What do you want that number to be called?
2.
No, that's specific. That's not like a name of a number.
Okay.
Oh, you want a. Okay, so you want a times x, and you wanted to add it to something times y.
Yeah, I have no imagination at all. B.
What do you want it to be equal to?
C.
Oh, jeez, you people are boring. All right, I can't help it. I'm going to like draw an eye and a smile on a C or something like this in the ears. Okay, so is this something that you're familiar with, I sure hope?
Yes.
Yeah, what does it look like geometrically?
Plane.
It's a plane?
In 2 spaces.
You don't have two-dimensional story.
So it's a line in two, so this is an important question right away, right? If we're in 2 dimensions, we agree this is a line, so side question. Okay. Question. In more dimensions. What is this? Okay, so just as a side note, if this were actually class, I would have an apprentice instructor and I'd say, problem set. I probably wouldn't have even written it on the board. I probably would have just said, oh, other dimensions, problem set. And the apprentice instructor would have written a problem out that would correspond to something like this, so that by the time we got to the afternoon, we would have it sitting around there. So wait, you said this is a line. That's weird though to me because, when I think linear, I think line. So let me tell you a definition. Linear. Linear means if you have f of x plus y, that's equal to f of x plus f of y. This is the definition of the word linear. And if you have f of alpha x, that's equal to alpha f of x. And so I have a question for you now. Is a line linear?
Did you want to talk about affine hyperplanes or linear hyperplanes?
Well, they don't have words affine and linear yet, right? They learn that in like 10 minutes from now, right? So I've just given them linear, yeah? Okay, so this is 10 minutes, all right. So this is just to give you a demonstration of the kind of thing we would do. But I'll tell you that in reality, what actually happened last year when I posed that question was they said, we need a coordinate system. And I said, okay, what does it mean to be a coordinate system? And they said, after approximately 10 minutes, I think, based on what I saw in the notes, because they take notes and they keep them. It took about 10 minutes maybe to come up with the fact that a coordinate system should describe every point in space uniquely. And so then, for the rest of the time that we concentrated on linear algebra, we're constantly asking this question, can you prove your representation covers everything? Can you prove that your representation is? Okay.
Can I ask, even though I'm not supposed to, a question, you can repeat it? What about polar coordinates?
What about polar coordinates?
But, I mean, their criteria was represent every point uniquely. You can't do that in polar.
Well, so
They're going to throw them out, or they don't know about them.
they actually mostly do know about polar coordinates, and for this purpose they don't care. Because polar coordinates are in 2 dimensions, and by this point they're trying to think in as many dimensions as possible, so the question just didn't come up. But if it did, and somebody said, but I don't think you can represent things uniquely in polar coordinates, I would say, problem set. And then there would be 1 or 2 problems written saying, can you show that this is not unique? Or is it? Which way does this go? And then, why is this called a coordinate system if it doesn't meet our definition? Yeah. Other questions? Or a blather? Okay. So, one question people sometimes ask me is, okay, so you have this very, very special situation at Mathley. How can you possibly do something like this in a college classroom? So you have some big differences in a college classroom, right? You have shorter classes at Mathley. I've got at least 3 hours in a row, if not 4. I have like maybe 50 minutes or like an hour and a half. I don't have problem sessions at college. I can't just arbitrarily decide that they're going to put in a few more hours. I choose when I teach in college to have a textbook, more for backup than for anything else. But the major tool that I use to sort of mimic this idea of generating problems and having them be in problem sessions is this idea of a running list. So anything that comes up during class that doesn't seem like it's the perfect best use of time at that second, gets added to the running list, by which I mean I say, add that to the running list. Everybody starts writing it down. It tends to keep students focused on the big goals because of this sort of enforced review. Like every couple of classes, I'll be like, make sure you look over the running list and see if there's anything you can now work on that you couldn't work on before. You can put on questions of all sizes and significances. That means everybody can make progress on something on the running list. And if students are getting stuck on big questions and you think they could be making more progress, you as an instructor can add parts to the running list yourself to say, okay, I'd like to add the following to the running list, something that's broken a problem down into more accessible parts. The way I deal with having shorter class meetings is I usually start with student summaries of solved problems, new ideas, new questions, by which I mean, in reality, what I do is I walk in and say, what do you got? And almost all the time after the first couple of classes, a student will say, okay, so I have a question, or so I have a thought on one of the problems on the running list, and they'll just go up to the board and start talking about it, and then the other students will join in, and then class will happen. The way I deal with not having problem sessions is to basically, every once in a while, say, your assignment for next time is to just work on the running list. Part of the point of having a textbook, by the way, is if they don't have the tools to answer the questions they're trying to answer, I can say, read section 4.3 in the textbook for next time and try problems 1, 2, and 3. And that'll give them some language, maybe. And then they'll be able to use this language to attack some of the problems on the running list that they were having trouble with before. So I think that's all the things I needed to say. Is that true? Yes! Okay. So you can ask me whatever you want, and I'll try to answer it. And now, actually, yes.
Hi. My name's Tom Hall. I'm also an instructor at Mathley. And I just wanted to mention, because I think you forgot to, that what you all did with Sarah-Marie's method of interrogating you about, finding the intersection points of planes, we're beginning to develop the concepts of span, linear independence, and basis. And that's the way, at least in Mathley, we try to, develop those concepts from an inquiry-based perspective, right?